So the ETC itself is generally the entry point for proposal planning. If you skip using the MTVT, right, you have a target that you know is going to be visible in the upcoming cycle, you can jump into the ETC to determine feasibility by estimating the signal to noise ratio for a given set of instrument parameters, and determine the time required to achieve your science goals. Looking for basic ETC usage, please watch the videos, watch the previous JWebbinar, look at the documentation. There are a lot of resources for the ETC. There's also an ETC help desk, a specific ETC help desk. And we'll be talking about some specifics for solar system observations. So now we're in the ETC. Typically you want to log in so you can save your workbooks that you're using. Since this is just a demonstration, I'm going to be doing work anonymously, so you can't see all of my workbooks. So when I work anonymously, there's nothing here, right? There are no previous workbooks. I'm going to create a new workbook, and then I'm going to load it. So now once we're in here, so here's the ETC. And if I go to, you come in on the calculations tab, but if you're setting up a source, you'll want to go to the scenes and sources tab first. I'm going to click on the default scene and the default source. So now I have these selected. We see a little cartoon image of a point source down here, and we have a flat spectrum. Those are the default options. Now I want to show something specific to solar system observations. On the shape tab, so in the source editor, for editing this source, we go to the shape tab. The default is a point source, but we can select an extended source as well. Then we get a bunch more options. The flux distribution is automatically set to a 2D Gaussian, but what we're looking for here is the power law. And you can see here in the scene sketch, the little cartoon down here, the power law gives a flat flux profile out to a certain radius, which is set here as the core radius. And then beyond the core radius, we have a decrease in flux as a function of an input power law index. So this was added to the ETC to support comet observations in particular, where you have that bright core of the coma with the nucleus, and then the coma decaying outwards. Unfortunately, you can't do anything except a circular source, so you can't do an extended or an elliptical source. It's only circular. So I forget that comet from 20 years ago or something. Was it Holmes? I think that was just a giant sphere puffed out like that. So useful for that, and also in general for any comet observation, just not quite the same shape. You should get reasonable results though. Yeah, that's the power law flux distribution for comets. I would like to now show, so I'm going to no longer use this default source. I'm going to create a new scene. I'm going to create two new sources. And I'm going to add, continue. I'm going to add these sources to the scene. And I'm going to demonstrate now how to set up, for instance, an asteroid that has both the reflected and the thermal component. So how to get both of those components in the same target essentially. And to do that, we would need two sources to achieve this goal. So for this first one, let's change the name to asteroid reflected. On the continuum, I'm going to select the Phoenix stellar models from this drop-down menu, and then the G2V model, right, to represent right? The reflected component of the target, the sunlight reflected off of it. And then renormalize, set it to 18 Vega Mag in K, and then save. So now you can see the different source spectrum here. The scene sketch remains the same. We actually have 2 point sources on top of each other. And for the reflected component, we now have a G2V model normalized to the brightness of the target. For the second source, let's rename it Asteroid Thermal. And we'll instead here select an analytic spectrum, the black body option. And we'll set it to the temperature of reasonable temperature for an asteroid, 225 Kelvin. And if we don't renormalize, we're going to get a crazy flux density. So we do need to renormalize this still. Set it to 1 millijansky at 10 microns. And we'll click save. It's called the scene asteroid. This will be asteroid reflected. And this one will be asteroid thermal. Okay, there we go. We have, if I check both of these boxes, you'll just be able to see, and this is not on a log scale, but we'll be able to see both the reflected and the thermal component for the object. The scene sketch, as I said, is 2 objects on top of each other, which is what we want in this case, right? We have the same 2 different components of the flux for the same target. Yeah, so we've now generated this this scene with 2 sources to model an asteroid. You can of course do the same thing. For instance, if you wanted to use the power law distribution, you could add a point source on top of the power law distribution to model nuclear emission, things like that. There's a lot of different ways to customize this and make sources useful for your science. But right now, just showing the basics of how to set some of this stuff up. For the next demonstration here, let's look at a workaround for bright sources. So let's create a new scene and a new source. I'm actually going to set this as the default. I'm going to add this source in. So in the ETC, when you're performing a calculation, there's a fixed field of view that the calculation is performed in. And this is to reduce the amount of time it takes for the calculation to run. Right, the larger the scene, the longer it takes to run that calculation. So in a lot of cases, you end up with these postage stamps where the calculation is run that is not anywhere close to the field of view of the actual instrument itself. So for instance, I think NIRCam is a few arc seconds on a side. You can expand that to make it larger, but after a certain point, it doesn't get any bigger. And it doesn't come anywhere close to the full field of view of NIRCam. So in that case, you can't actually create an object that models Jupiter perfectly, right? Jupiter is 45 arc seconds across. It's going to be larger than any of the scenes used in the ETC. On top of that, the point spread functions that are used don't change size, right? So the PSFs that are generated fit the default size of the aperture chosen in the ETC based on the instrument. So even if you do expand the scene that the calculation is using, you're not actually getting convolution of that PSF appropriately across the scene. So if we want to determine the amount of time needed for an observation of Jupiter, for instance, we have to do a little bit of a workaround here. for large bright sources. So let's call this giant planet. We'll give the same name to the source. We'll only use one source here. Click save really quick. So we see the updated information here. And we'll go again to the shape tab and select an extended source. In this situation, let's go with a flat source. So as you can see in the scene sketch, there's no longer any kind of tapering towards the edges of the source. This is just a flat flux distribution across the entire source. And for the normalization choice, we'll choose surface brightness in square arc seconds. Now what we want to do is create a flat extended source that has an area of 1 square arc second. So for both the semi-major and semi-minor axes, we'll put in 0.564 arc seconds so that you square that and multiply by pi, you get roughly 1 square arc second. Go to the continuum tab here, do the same thing we did before, selecting the G2V, so we're looking at the reflected component only this time. And we'll renormalize. You'll notice it's updated to be per square arc second. So it's right now millijanskis per square arc second. Let's update this to be janskis, and we'll set it to 1 Jansky at 2 microns. And click save. So now sketch, spectrum, and we can use this in calculation. So we'll leave the Scenes and Sources tab, go to the calculation, create a NIRCam shortwave imaging calculation. And because I've set this as the default scene, it'll automatically run it. Go to the strategy tab here for the calculation and set the aperture radius to match the size of the target that we created. And we'll have to update the background as well. Okay. And you can see from this that there is some pretty bad saturation because the target is so bright. Let's see if we can change that really quick. Do something really short. Let's see if we can avoid saturation. Okay. Well, this is a very bright target. Obviously, for Jupiter, we did observe Jupiter in commissioning successfully without saturation occurring. So to make sure you choose the right filter, right? Obviously not a wide filter. Probably want a narrow filter, short integration times, things like that. But the important point here is the workaround. There we go. Right, the workaround here for giant extended sources. We can see the apertures are now drawn. So you have the orange circle representing the aperture that we're extracting flux from, and then the dashed lines here showing where the background is computed. And you can tweak these values based on what you see here to make sure that you're not subtracting any of Jupiter from itself. You're going to get very high signal noise when doing these kinds of observations, right? This is saying it's an SNR of almost 3,000, which I don't think is actually physically achievable. But the point is, it's going to be pretty. You're going to get the signal noise you need, and most of the time you're just worried about saturation. So, all right. There's one last thing to show in the ETC. I want to discuss a little bit how to set backgrounds for moving targets. So we have, for the calculations, we have a background tab here, and you can specify a position on the sky, you can specify a date, or you can specify either low, medium, or high configurations. So that corresponds to 10th, 50th, or 90th percentile of background over the course of the year for that specific position, because the background will change over time over the course of the year. Now, this is most useful, obviously, for observations where you know where the target is, aka fixed sources, and specifically if you know what date the observation needs to occur, right? So an extrasolar planet transit, probably pretty useful to specify the position and the exact date that you want to observe it. It's obviously not the case as much for solar system targets. They're moving. You don't know when the observation is going to happen most of the time, right? Unless you're putting a time critical constraint on it. So in general, what I like to do is set the background configuration to high to get the most conservative estimate of the signal to noise for my target. A lot of the targets are also near the ecliptic, where there's going to be a lot more background contamination. So that's my personal choice. You can also provide a rough array and deck for the target. If it's a slower moving target, you can give an idea of where the target's going to be in a particular visibility window. But in general, you're not going to get, if you're not quite spot on to where the target is observed, the spatial scales over which the background varies is a few arc minutes, I believe. So you're not going to miss out on anything by choosing one particular position along the ephemeris for your target. All right, so those are some of the specifics for the ETC. There's not a whole lot extra. The learning curve more is using the ETC itself, and not as much the specifics for solar system observations. But a lot of the things that I've shown here, the power laws, reflected in thermal components, the large source workaround, those are all summarized, or they're all replicated in the solar system sample workbook. So in the sample workbook dropdown at the very bottom, solar system sample workbook, it's available to everybody to use, and you can load that, and it has a lot of the same things that we walked through. So in some cases, I actually used similar numbers, similar values to help set up the walkthrough that I just gave. Replicated what was in this workbook, so you can come here and look at this to get more information, or to remember what we did here. There is also an example science program workbook for solar system observations. So number 34, NIRSpec IFU and fixed slit observations of near-Earth asteroids. So this comes with accompanying JDocs pages that walk through how to set up the ETC workbook, how to set up the APT file, right? Provides the science case. And in that science case as well, there's a lot of information on when it's a good idea to use target acquisition and when it's a bad idea to use target acquisition, because there are bad times to use target acquisition.